Welcome to another episode of Bull with Boone. Bull with Boone. Today I want to talk about space. I want to talk about the galaxies, Milky Way, and the one we live in, Milky Way, and Andromeda. These are two large galaxies. There's a couple of small ones in between, but the two large ones in our neighborhood, stellar neighborhood, is the Milky Way and Andromeda. When they're about 2 million light years apart, and in the far future they are going to go through each other. They're going to collide. So the question that comes to mind is, what are the chances of stars bashing into each other? Well, what I'm going to try and illustrate to you here is that the space between the stars is so vast that the chance of collisions are very small, in spite of the fact that there are billions of stars, 100 billion, 200 billion in Milky Way, and maybe more in Andromeda. In any case, nevertheless, so what I've done is I've now said let's take the Milky Way and we work from that. Let's say Andromeda is similar to that. So now I'm going to average out the Milky Way. In the center, it's far more dense than the outside. So if we average it out, you'll find the stars are about 5 light years apart. So there'll be a star here, 5 light years throughout the entire galaxy if we average it out. Also, the size of these stars are going to be about the size of our sun. That is about an average size star. So there's some more massive ones, and there's some tiny ones. But the average size star is about our sun. So what I've gone and done is, I've said, right, to get the scale that we can try to understand these massive distances, is I've used a marble as an example, which is 13 millimeters in diameter, and I've used a squash ball, which is the same as a table tennis ball, that's 40 millimeters in diameter. I've used a tennis ball, 68 millimeter in diameter, and a soccer ball, regulation soccer ball, which is about 220 millimeters in diameter, or 0.220 meters. Right, so what we do is we take our sun, which is about 1.4 million kilometers diameter, and we shrink it down to the size of a marble or a tennis ball. Then this distance that we have here, which is a 5 light years, we're going to shrink that as well on the same scale. Then you'll find that the stars, which are on average 5 light years apart, now you shrink them down to the size of a marble. Let's work on a marble for a while. You shrink it down to the size of a marble. Then you also have to shrink the distances. So what's the distance now of these two marbles? My first thought was 100 meters, 200 meters, I wasn't sure. When I did my calculations, it turns out 442 kilometers. That's how far these two marbles are. So if you take a soccer ball, which is 220 meters, we shrink the sun down to the size of a soccer ball. The two soccer balls, when you shrink that distance down where these two soccer balls are, you'll find that's 7,500 kilometers. That's wider than the United States. That's how wide. That's where these soccer balls are. So that's on average. That just illustrates how much space there is. So then what I did is I did another example. I said, okay, let's go to an extreme. Let's take the largest known star. The largest known star is UY Scuti, and that is so big that if you put it where our sun is, it'll be so big that Mercury will be inside that, the orbit of Mercury. The orbit of Venus will be inside that. The orbit of Earth will be inside the sun, all the way Mars, Jupiter, all the way to Saturn. That's how big the star is. What I must also remember is it won't be as dense as our sun, well, on the outside, because as it gets so big, the gravity is much less, and it's just a big star. But we're just talking now distances, diameters. So that's how massive this big star is. Right. So if we now, we'll make we'll take that star, right? What we'll also do is the densest region of the Milky Way happens to be obviously the galactic center. Now, the galactic center, there's in the Milky Way, there's a 0.006 stars per cubic light year. But in the galactic center, there's 288 stars in a cubic light year. This is if you take the galactic center and you just go out, say, about 260 light years. Because the entire Milky Way is about 100,000 light years wide and about 1,000 light years thick. But if you just take the core, the center, where there's obviously the most dense, you'll find 288 stars per cubic light year. So what I've gone and done is, I said, right, we'll use this as our star instead of the sun, and we'll still use our marbles, table tennis ball, squash ball, tennis ball, and soccer ball. And then, but now, we'll shrink those distances now. But then the distance between between stars at that density turns out to be 0.188 light years, as opposed to 5 light years if it was averaged out. But with that density, there's a star every 0.188 light years. So now, if you shrink them down, you shrink this big massive star down to the size of these marbles and so on, then the distances, that's the question, where will the distances be then? Then it turns out, let's just take a tennis ball, which we shrink from this massive star, which is greater than the orbit of Saturn, we shrink it down to a tennis ball. Then you'll find the tennis balls are 50 meters apart, which is half a rugby field or half a football field. That's where these two tennis balls are. In spite of the fact that we've made it so incredibly dense and we've gone to such an extreme, because we've taken the densest star we know about, we've taken the center of the galaxy, and we shrunk that, and we still end up with these two tennis balls being 50 meters apart. So it just shows all the empty space that we're dealing with here. Also, if we just look at the sun size, we can't do it with this massive star, but if we take the sun, and we had these distances here, like the tennis ball was 2,300 kilometers before the next one. But now the question might be, where's Earth and our planets? Well, it turns out the Earth is only, on the tennis ball, it's 7 meters away so the tennis ball is here, and then 7 meters away is our Earth. And that'll be so small, it'll be less than a millimeter in diameter compared to this tennis ball. And Saturn, which is the third furthest planet, that would be, that is 71 meters away. So 7 meters would be the Earth, and then 71 meters on the normal, our average scale. In other words, where the tennis ball is 2,300 kilometers away, and the one's here, 2,300 kilometers there, 2,300 kilometers there, so on. But our Earth is going to be just nearby here. But that's all the space. So when these two galaxies collide, you can imagine, what are the chances of a tennis ball here, tennis ball 2,000 kilometers away, and so on, spread all over the place? And it's similarly in Andromeda, if they collide, what are the chances of stars being hit? Well, that's my story for today. I hope you have a good day, and tune in for the next episode of Bull with Boone.